Welcome back. This is lecture 58 in this course on Bayesian modeling. Topic of this lecture is indivisible difference models. Now this topic is not typically taught in a Bayesian modeling course, but the reason I'm taking this topic, and in my opinion this is an important topic, is because in behavioral sciences, let's say either you are doing some either economic behavior modeling or in cognitive science or linguistic experiments, right? We often have systematic differences across individuals in a population. Okay, so the kind of population we are dealing with, it's human population, right? And there are often individual differences between these individuals on certain parameters. For example, some individuals are faster at processing some information compared to others. Individuals can differ in their, let's say, working memory capacity, attention span. Okay, so they can differ in these latent parameters at the cognitive level. They can also differ in their, let's say, motor processing speed. Okay, so individuals can systematically differ. Okay, so whenever we draw the sample from a population, one conventional approach is just that we will calculate the average behavior of the sample and we will draw our inference based on the average behavior of the sample. For example, you have seen that all the hypotheses that we have been talking so far, they are about the population level behavior. So at the population level, whether there is an effect of frequency or not, we are interested in population level effects. Okay, but how do we measure this population level effect, or how do we make inference about population level effect? We make inference about population level effect using average behavior of the sample, that on average whether there is an effect of frequency on recognition times or not. Okay, now whatever inference we make from this group sample level behavior, basically samples average behavior, it could generalize to the population, but it may or may not generalize at the individual level. And what do I mean by that? So let's say on average, if you take a sample of 100 individuals from a population, okay, and that sample shows that there is a significant effect of frequency, okay, but does it imply that all individuals in the population show a significant effect of frequency? Okay, so you can think about the same question in the frequentist framework as well. Okay, it doesn't matter, it's regardless of kind of framework you use for inference, but this is what we often do. We draw our inference from the average behavior of the sample. In frequentist framework, you just calculate some summary statistic from the sample, right, and based on that you draw some inference. But a question that we should be asking is that whatever inference we draw from the average behavior, so let's say based on average behavior, we say that there is a significant effect of frequency on word recognition times in this particular Indian population. So let's say we make this claim, but does it mean that every individual in this population shows this effect of frequency on word recognition times? Maybe, maybe not. Now you would ask why this question is important. Why do we need to be concerned about individual level effects, whether all individuals saw this effect or not? It could be the case, and it is often the case, that there is some quantitative variability across individuals. There could be also qualitative variability across individuals. It could be the case that maybe 1/3 of the individuals do not show an effect of frequency, but we still see this effect at the average group level, because whenever we draw a sample, at least 2/3 of them show the effect of frequency. So on average, we would still find an effect of frequency. Okay. So even if, let's say, on y-axis I'm representing each individual subject, on x-axis it's the frequency effect. So let's say beta z, let's say. Okay, so even though these effects might look like this, the subject level effects. Okay. So let's say subject level effects are like this. Okay. But when you would calculate population level effect, so let's say these are actual subject level effects, betas is. But when you calculate population level effect, the population level effect would come somewhere around here. This would be your population level effect. Now this is average of all these subject level effects. Okay, so this is your beta. Now based on beta, you can claim that there is an effect of frequency, because beta is significantly whatever, positive or negative, depending on whatever your hypothesis is. Okay, so there is a significant effect of frequency based on this population level beta. But do all individuals saw this effect? No. So why this is a matter of concern, or why are we asking this question? The reason why we are interested in this individual level question or individual differences is this, that whenever we are building theories about human behavior, we are building theories about behavior of a human being or an individual human. We are not building theories about some abstract average ideal population that does not exist. Okay, the average population does not exist. What exists is actually, in reality, what exists are these individuals, right? And if these individuals differ in terms of, let's say, frequency effect or certain other parameters, right, then there might be something systematic about the underlying generative process. Okay, so in a way, if you draw inferences based on the average behavior, you might lose on some theoretically important information. So there are two ways around this. So let's say I will model every individual and I will figure out why exactly they show this much frequency effect. Okay, and let's say I have figured that out, that why certain individuals show a low frequency effect, why certain individuals show a high frequency effect, why certain individuals do not show a frequency effect. Let's say I have figured that out. Wouldn't that be more informative compared to drawing inference from the average, which always says that there is a frequency effect, and we are not moving forward in theory that why there is a frequency effect, okay, which can be investigated if we look at individual differences. Okay, so these are the two reasons why we are interested in individual differences. One, the average behavior, so the inferences drawn from the average behavior may not be generalizable at the individual level. So whatever we have found based on average behavior, it may or may not generalize at the individual level. So certain individuals may go in opposite direction compared to what we saw at average level. Okay, consequently, whatever theoretical insights we draw from the average behavior, okay, it may not be sufficient, or it may be theoretically misleading, because individuals saw something else, right? So if we instead, rather than doing this, if we model, let's say, individual differences, we might be able to this might lead to more theoretically informative insights, right? So it basically it can provide more information about the underlying process if we model individual differences, right? So this is one reason. Second, ultimately we are interested in building a theory of how an individual processes language, or how an individual processes decisions about that. So we are interested in theories about an individual human, not about some abstract average population. Of course, theories about abstract population, they help in knowing more about humans, but ultimately we are interested in theories at the individual level. Okay, we of course have some constraints. That's why we have been building theories at the population level in terms of testing and other things, right, in terms of power, sample size and all that. But that does not mean that we should ignore individual level variability. Individuals differ and they may systematically differ, and that might be theoretically informative for whatever theory we are building, and it is also more um, aligns more with natural direction of the field. Basically, naturally we are going to build theories at the individual level. Okay, so consider this. Let's say you want to predict um, let's say effect of frequency on a word recognition task, or let's say you want to predict any behavior on a task, right? Now there are two ways around this: that you build an average population level model and you predict the behavior, you predict the average behavior of the sample. Okay, another way is this: that you take, let's say, 100 individuals from the population. For each individuals you take some independent measurements. So let's say for each individual you measure their processing speed, their working memory capacity, attention span, their education background. So you take these multiple independent measurements from each individual, let's say 7-8 measurements, and based on these measurements, let's say now your model predicts that individuals processing behavior on a task, right? Now you are predicting an individual's behavior on a task based on the history and the other measures from the same individual. Okay. Now, this is a much more informative model as well as much more utilizable model. Okay. This is much more useful model. For example, especially in the context of medicine. So, in medicine, we are often drawing inferences based on average behavior of the sample, and we are prescribing medicines based on whatever average inference we have. But let's say your model predicts that given particular medical history of an individual, certain kind of drugs should be prescribed more, or certain, let's say, salts should be prescribed more than others. That would be much more useful. Okay. Similarly, in let's say treatment of individuals with some cognitive disorders or language disorders, based on exactly uh, what kind of deficits they have, what is their language background, their proficiency, or whatever other measures we capture at individual at patient level, we can design their treatment much more effectively based on their individual history, right? So what I'm saying is that this is a complementary approach to the typical average behavior modeling approach that we take in cognitive science. Of course, in psychometry and some other uh, related fields, we often use this individual level behavior modeling approach, but not so often in behavioral experiments, right? But this is important for the reasons that I told, that, well, it is more theoretically informative. It can inform theories much more than just average behavior approach, because average behavior can be misleading sometimes, or it can be less informative. Second, this is our ultimate goal. We want to build theories at individual level. We would want to predict behavior of an individual given other uh, parameters from the same individual, right? So that's why individual difference modeling is an important avenue. And using Bayesian hierarchical models, you can do that in a very easy way, right? Of course, this wouldn't solve the entire individual difference modeling problem, but it would give you some direction. Okay. So what would happen in these models? These are basically Bayesian hierarchical models. There is nothing different. So let's say reaction time on a task on ith trial from jth subject comes from some underlying generative process f with some parameters, let's say theta and phi, such that these parameters are theta ij and phi ij. Okay. And now let's say theta ij is some function of some other parameters. So, let's say alpha j, beta j, and so on, right. Okay, so let's say alpha j and beta j, right. And phi ij is also a function of, let's say alpha dash j and beta dash j. Okay. Okay. So these are individual level parameters, right. This is just one example, by the way. You can have a much more simpler model. So let's say reaction time in ith trial for jth subject comes from some generative process with sub individual level parameter theta j and phi j, such that theta j comes from normal population level theta and tau 1, and phi j comes from normal population level phi and tau 2. But the reason I'm giving this example is that you can build hierarchical model for any kind of generative process, not just regression models. Okay, this is not a regression model, but we still have a hierarchical structure in this model. For example, this could be a simple drift diffusion model. So let's say decision time in ith trial from jth subject comes from a drift diffusion process with those parameters drift rate, non-decision time and all that, such that all those parameters drift rate, non-decision times are at individual level. Okay. But how do we do this? How do we use this for individual difference modeling? So let us call this varying theta and varying phi model. So in this model, both theta and phi vary. Okay, they vary by subject. So subjects differ in both theta and phi. Okay, but you can make an alternative assumption. So let's say f theta j phi j such that theta j comes from normal theta tau 1, but phi j is equals to phi. So phi j remains constant. So across all subjects, this parameter phi remains constant. Let us call it constant phi model. So all individuals are exactly same phi. Okay. You can also have more interesting model like this, that RT Ij comes from f theta j phi j such that theta j comes from normal theta tau 1, but phi j is actually equal to 0. It is same across all subjects, but the value is exactly 0, fixed. Okay. In this case, the model would estimate this value from the data. It could be positive or negative. In this case, it's exactly 0. You can call it 0 phi model. 0 phi model, and it also does not vary across subjects. In another version, you can have this model such that phi varies across subjects, but population level phi is 0. Okay. So this way you can construct different models. You can do the same thing with theta. So you can have a constant theta model, a 0 theta model, right. So this is one thing, that you can construct models of this type, that in one model you are assuming that this parameter phi varies across subjects. So let me write it like this. So let's say this distribution represents distribution of phi j's across subjects. So these are values of phi j. So let's say you take 1000 subjects, those subjects differ in their value of phi j, and let's say this is the distribution of phi j such that the mean would be phi. So I'm talking about model 1, varying phi model. Okay, so mean would be phi and the standard deviation will be tau 2. So this is one assumption. Let us call it the varying phi model. You can have another model which assumes that phi j remains constant across all subjects. So this model would say that phi j is exactly same for all the individuals, and it is at this point phi. Okay. This is called constant phi model. And you can also have a third model which assumes that actually all the individuals have exactly 0 phi. So, this is point 0, all phi j's are here. Okay. So, this is 0 phi model. So, these three models make different assumptions about how individuals are distributed in the population. In this model, individuals are distributed normally around this parameter, around this population mean phi. In this model, individuals have exactly same value phi. In this model, all individuals at 0 value of phi. Okay. By the way, this assumption that individual level phi are normally distributed, this is only one of the assumption. You can change this. What you can say, for example, is something like this, that some individuals have a very low value of phi, but most individuals have a large value of phi. So, it would be this kind of distribution. This is called a spike and slab kind of distribution. So, what is happening in this distribution? This is like a mixture distribution. So, most individuals have a low value of phi. Okay. Sorry, some individuals have a low value of phi, but a lot of individuals have a large value of phi. So, the distribution is not normal, it is like a mixture distribution. Okay. Then you can also make explicit assumptions if you want to do hypothesis testing. So, let us say something like, one is that all individuals have a strictly positive value of phi. So, this is phi. So, individuals vary in terms of this parameter phi, but all individuals have a positive value of phi. Here is 0. So, this is one model. So, let us call it all positive model, right. And another model can assume that most individuals do show a positive effect, but some individuals do show a negative effect as well. This would be called most positive model. Okay. How would we represent this? So, this would be phi j comes from normal, which is truncated at 0, phi and tau 1. This would be phi j comes from normal, phi tau 1. So, this allows some individual to have negative value, or you can more explicitly specify this. Then you can have a model where all individuals have negative value of phi. Okay. So, this would be phi j normal truncated such that all values are negative, right. And then you can have all individuals have negative value of phi, but they have same value. Okay. So, basically I have shown here approximately 8 models. All these models are making different assumptions about how individuals are distributed in the population. Now, you can compare these models to make some inference about how individuals differ. Okay. So, if you can ask this question, that how individuals differ in the population, exactly how individuals differ. How you can answer this question? So, let us say you compared a model which assumes that phi j comes from positive normal phi tau 1. Let us say this is model 1, which assumes like this. Model 2 assumes, so this is all positive model. Model 2 assumes that it is all positive, but phi j exactly equals to phi, they are all constant, versus model 3, which assumes phi j can take any value, negative or positive. Okay. And let us say model 1 does better than model 2 and model 3, then we can make a claim that individuals do differ in this population, but all individuals exhibit a positive value of phi. Okay. So, basically we are drawing inferences about how individuals differ in the population based on model comparison between these individual difference models. These three would make three different individual difference models. All other parts, the likelihood function will remain the same. Our assumption about phi j differs across these three models. Okay. So, we can compare individual difference models. Basically, these are Bayesian hierarchical models. So, we can compare hierarchical models under different assumptions about individual level variability, about different assumptions about how individuals differ, right. So, we can build different models which make different assumptions about how individuals differ in the population, and we can compare those models to draw inferences about how exactly individuals differ given the data. Okay. So, this is a very important tool that you have. Of course, a much more informative approach would be this, that you can measure, let us say, these individual level phi j using some independent experiment, and then plug in these values of phi j in your model, and then try to predict the recognition time on a task, right, or the reaction time on a task. That would be another approach. Okay. But this is a handy approach. This you can do with whatever kind of data you have. You basically just use the same generative process that you are using for modeling your average behavior, but you make different assumptions about your parameters of interest, that how individuals can differ in terms of those parameters. Okay. And then compare those models under different assumptions about individual differences. That would give you very interesting insights about how individuals differ in this population. Now you can generate future predictions, that let us say this model 1 does better than model 2 and model 3, and what does model 1 predicts, that all individuals in the population show a positive phi. Now you do future experiments and estimate what are individual level parameter phi, and if they all show positive, then your model 1 has predicted it already, right. Then your model predictions are good. Okay. This way we can also test these individual difference theories or individual difference assumptions using future data as well. Okay. So, we can predict what will happen in the population in the future. So, remember, you can generate two kind of actually you can generate three kind of predictions about future data. One is the prediction we are often interested in, prediction about predict average behavior of the sample. So, for example, average difference between two conditions. This is one kind of prediction we are interested in. So, model often generate this prediction. Second kind of prediction could be this, predict behavior of a particular individual given other independent measures and history of the individual. So, if you get other independent measures like working memory, processing speed from the individual, and you use these measures to predict that individual's performance on the task. So, a particular individual's behavior. Okay. But you can also have a third kind of prediction, which is again about the population, but a different kind of prediction, right. In this case, you are predicting average behavior at the population level, but in this case you can predict distribution of individual level behavior in the population. This is exactly what we were discussing. So, for example, you can have a model that predicts that all individuals in the population would vary in their effect size, but they all of them would show a positive effect. So, that is a prediction about distribution of individual level behavior. Okay, you can have another model which predicts that all individuals would show exactly same positive effect. They are constant. Another model that predicts that most individual would show a positive effect, but some would show a negative effect. So these are predictions about distribution of individual level behavior in the population. And in order to test the prediction of these models, you would need to draw inferences from individual level behavior in your sample. Okay. All right, I'll stop here. So this is it about individual difference models and how you can compare individual difference models using Bayesian hierarchical modeling. Okay. In the next lecture, we will see that how to implement Bayesian hierarchical models in R using the BRMS package that we have done so far for regression modeling. Okay. All right, I'll stop here and see you in the next lecture. Thank you.